Good morning, good afternoon, and good evening, everyone. So today we're going to be going over a new topic here in our calculus series. We're going to go over double integrals over rectangles. So let's get a heads up. Okay, I'm just trying to kind of look through what the homework's going to be, just so that I can do this a bit quicker and just go ahead and recognize these patterns and then just go for it. Okay, so in much the same way that our attempt to solve the area problem led to the definition of a definite integral, we now seek to find the volume of a solid, and in the process, we arrive at the definition of a double integral. And so if we're trying to find the area of a real valued function, we'd use a single integral. But here in this case, if we're trying to find the volume of a surface, a quadric surface, a solid, then we want to use a double integral. So let's do a brief review of what exactly was a definite integral, right? So just a brief review of what this was. Definite integral. So what this was, so this is used for a single variable, right? And so we're saying if f of x is defined for some bounds ab, then we start by dividing the interval ab into n subintervals. So we're kind of cutting out the pieces in that interval ab from x sub I minus 1 to x sub I of equal width, and that's delta x. And then we choose sample points x sub I in these subintervals, and then we have a Riemann sum, right? So that's our first definition of an integral. So we get a summation from I starting at, I'm assuming this was 1, all the way to n. And then here we're getting sampling points, delta x. So that was the definition of our Riemann sum. And then once we take the limit of those Riemann sums, so because those are rectangles, right, in that curve. And so once we get the limit of all of those rectangles, we keep on going and going and going and going until the rectangles are super, super small, until we get the exact area of that curve. Then we have an integral, right? So what we basically mean is the integral, or a definite integral of some function, is basically the limit of their Riemann sums, right? That's the basic definition of an integral. And then we have some special cases where, let's say, our function is greater than or equal to 0, then it's basically just the sum of the areas of the approximating rectangles, and our integral represents the area under that curve from A to B, right? So those are some basic stuffs. Now let's proceed to the actual topic, which is this concept or this idea of volume and how we can apply double integrals to get such a volume of the surface in calculus 3, so in 3D. And so in a similar manner, we consider a function of two variables defined on a closed rectangle, right? So here, how do we define boundaries? That's the other issue that we have. So we actually define them. So let's say we define a function f of two variables. On a closed rectangle. So here we're going back to that idea in our previous video on bounded regions. That's our domain, right? So let's say this is R from A to B by C to D, right? So that's our bounded region. And this is basically a set. So it's the set of all points x, y. Okay, they are in 2D. And we're saying that they're bounded by, so x is bounded by a to b, and y is bounded by c to d. So this is actually the mathematical definition. I'm gonna go ahead and share a screenshot of this thing, of what exactly I'm talking about, because it's easier to visualize these things rather than just writing them out in math. At least for me, I prefer visualizing. Some people prefer the math definition because they're more used to it. Depends on the person. Okay, so here's the R, right? Here we see this is bounded by a to b, and that's our x value. So this is our x-axis. We have a here, we have b here. A, b, and a. Similarly, we have our y-axis. That's our c and d, c and d. And so this is our bounded region. And so if we put them up like that, right? Then we bound, or we impose boundaries in our quadric surface. Here, this is our quadric surface, this thing. And it has a function z equals f of xy, which means it's an explicit function. And yeah, that's basically the idea. We're bounding it by some rectangle R. This is a rectangle R, the green one. What else can we say? Our goal is to find volume S. So we want to find the volume of this thing. How do we do that? Well, we use a double integral. I'm just going to say it. Okay, so the first step is to divide the rectangle R into subrectangles. And we accomplish this by dividing AB into M subintervals, xi minus 1 to xi, of equal width delta x equals b minus a over m. So here we're just going to divide it, right? So we want to find volume, oops, the volume of our surface S, right? So how do we do that? Well, first we want to divide this R. You want to divide that. So divide R into subrectangles. What do I mean? Well, we choose intervals, right? So here we divide the interval. Divide AB into M subintervals. Subintervals, right? And then we also, okay, yeah, into intervals x sub I, what's this? X sub I minus 1 all the way to xi. So we basically just want to keep on dividing them. And they're equal width, right? They're of equal width delta x. And our delta x is basically when we subtract our upper bound and lower bound, we divide it by m, we get the equal width, or the width of each little piece there. And we also do the same thing for our C to D interval. So in Calculus 2, we only did this once. The difference now is we're doing everything twice. That's it. We're doing everything twice. And so there shouldn't be any confusion. They're basically just going to do everything twice. I think. I think we're going to do everything twice here. So again, we do the same thing for our intervals C to D in our y-axis, right? Let's divide them again into some subintervals. Here we'll call it n. And This is from y sub I minus 1 all the way to y sub I. And they're of equal width again. We'll call it change in y or delta y. So it's going to be delta y. When I subtract both my upper and lower boundary, I divide it by n, I should get that. And by drawing lines to the coordinate axes through the endpoints of these intervals, we form the subrectangles. Okay, when I'm looking at it, I look confused. By drawing lines parallel to the coordinate axis through the endpoints of these intervals, as in figure 3, we form the subrectangles. Okay. So after that, we basically form subrectangles. When we draw a couple of lines parallel to those. Because here what we're doing basically is we're going to do this. Oh, shoot. I made it. Okay. Pretend those are straight lines. But basically, we're going to do that. We're going to cut everything, right? And so the moment we do that, so we're going to form subrectangles. And how would these, in a mathematical sense, this is how it looks like. R sub ij is x sub I minus 1 all the way to x sub I. And then we multiply that with our y. What am I doing? And then there's going to be a sum set. So it's going to be some set where x is in between these intervals. That's all I'm saying. So x is going to be, going to be in between each of these intervals. And y is also going to be in each of these intervals. In this interval. Right? That's the mathematical definition of it. How does that look like? Okay, actually, wait. And we're saying that each have an area. Let's say change in area A. I don't know how else to define it. We're just multiplying our x and y, right? And so let me actually share a screenshot of what that exactly looks like. So that would look something like this, right? Cool. So we have that, right? Here we get the area of each of these things. Now, what confused me the most was what in the world are these small points? And they're so random too. Well, these are sampling points, right? And we're getting the area of all of these random things here. So I guess that's what makes it a bit difficult. Okay, if we choose a sample point, so say we choose, I don't know, this sample point, right? Because it's already telling me to look at that. In each R sub ij, then we can approximate the part of S that lies above each R sub ij by a thin rectangular box or column with base R sub ij and height, where we just plug in the function of those two sampling points. And so the volume of this box is the height of the box times the area of the base rectangle. So again, let me quickly show how that looks like, or let me quickly read it again. So basically what we're seeing in this picture right now is we're dividing R into sub-rectangles, right? So this is my boundary A, B, C, and D. And so we have that green rectangle, just like the one here. We impose that this is going to be the XY plane, right? This is the XY plane. And this is our rectangle, R, our rectangle R, the green one. And we have x1 all the way to xn. We also have xi minus 1, xi, just to denote that our change here is delta x, right? And similar to our y. And then we pick some points here. So these points are what we call sampling points. These black dots here. And basically what the textbook is trying to say is that if we choose a sample point in each R sub ij, we can approximate that part of the surface that lies above each R sub ij. So the part of S that lies above each R sub ij by a thin rectangular box or column with base R sub ij, right? And so that's the base. This is the base. It's an area, which is R sub ij. And we're going to also think about its height. So how high is it when I plug my sampling point into a function? So that's a function of two variables, right? Because I plug it in here, ij, ij. That would give me my corresponding height, just like a previous integral in Calculus 2, where we worked with real valued functions. And so the volume of this box, of that particular small box, is the height of that box times the area of that base rectangle, right? So let me just completely write it out. So choose sample point. That's going to be some xij sample, some yij sample. We're going to choose one in each region R, or I don't know what you call this. I'm pretty sure you call this some sort of region or bounded region. So in each Rij, this is one Rij, this is another Rij, another Rij. So we choose one for each. We choose one of these points for each. And funny enough, if we manage to look at all of them, there's only one black dot in each green rectangle. Believe it or not, these are not random. Well, yeah, they're random because they're sampling points. But if we look at each rectangle, there's always going to be one dot. And those are the sampling points, right? So we're going to choose that sampling point in each Rij, approximate the part of S that lies above each Rij by a thin rectangular box or column with base Rij and height. So approximate the part of S that lies above each Rij. Above each Rij. Above by a thin rectangle. I can't visualize that. Okay, but here we choose that and then we approximate it. I will see an example. I can't visualize it now. Approximate part of S that lies above each Rij. And then what's the next thing? So that part is a thin rectangular box or column, and it has that base Rij. So we approximate it with that. as well as its height, and the height as well. So this is, we just plug it into the function, our sampling point, to get the corresponding height. And then from there, the volume of this box is the height times the area of that particular triangle. So the volume of that particular box is the height. So it's the height of the box times, oops, times area. In particular, the area of the base rectangle. And so that's going to be our height function. And these are sampling points times my area. And if we follow that procedure for all the rectangles, then we add the volumes of the corresponding boxes, then we get an approximation. So that means an approximation of that volume would be a Riemann sum, but it's a double. Because here, now we're using two integrals, right? Oops. Yes, that's the only difference. We're using two integrals. And so this double sum means that for each subrectangle, we evaluate f at the chosen point and multiply by the area of the subrectangle. So we take an f point, multiply it by its area, and then we keep adding, or we do a Riemann sum. So here's how it would look like. Okay, now this is better. If we were to go back to our original example, the one that was previously shown, this visual here, let's look at that again. This is how it would look like. So we have our f, which is this. That's our f of the sampling point. This black dot is our sampling point. And then we multiply it by, so we multiply that with the change in area, right? And once we do that, we get something like this. And that's basically equal to this. So we have a couple of rectangles, and we take their Riemann sum, and we get something like this. And then from there, now how do we get the exact area? Well, our approximation there becomes better and better as our m and n, so m and n here, as both of those become larger. And so we just take their limits. And that's how we get the volume of our quadratic surface, right? So here we have V, the volume is the limit as our m and n approach infinity. So we have our m, then we have another sum here, summation. And this is when we look at our sampling points. Oops, my bad. Yeah, so this is a calculus 2 thing. And then we get that change in the area, right? And so we use the expression above in this equation 4 to define the actual volume of that solid. Now here's where integrals come into play. So the volume of that solid S that lies under the graph of F and above the rectangle R it can be shown that this definition is consistent with our formula for volume in the previous section. And so the limits of the type that appear in equation 4 occur frequently, not just in finding volumes, but in a variety of other situations as well. As we will see in section 15.4, right now we're in 15.1, even when f is not a positive function, we can make the following definition. So here's the definition of it all, like how it works for everything. So the definition is that we get the double integral of f over the rectangle R So it's basically this. So this is an indefinite integral, f of xy, change in, or no, here we do a d. So that's the change in the area, which is the same as our limit of Riemann sum, right? Here we do this. Right? So that's that formal definition. Okay. Now, we have a precise meaning. I'm not going to go through that though, but basically it's integrable if it's continuous, right? Okay, I'm going to completely skip all of that. Let me see if the limit in definition 5 exists. Okay, so if the limit exists, then the function is integrable. What else? In fact, the double integral of f exists provided f is not too discontinuous. What does that mean? If f is bounded on R, that is, there is a constant m such that the absolute value of that function is less than or equal to m, except possibly on a finite number of smooth curves, then f is integrable over R. Sample point can be chosen to be any point in the subrectangle Rij, but if we choose it to be the upper right-hand corner of Rj, then the expression for the double integral looks simpler. By comparing definitions 4 and 5, so I'm going to write this one, actually. Okay. So here, I'm going to say that if my function of two variables is, let's say, greater than or equal to 0, what does that mean? It means it's above my xy plane, or it's at my xy plane. Then my volume of that quadric surface that lies above the rectangle R and below the surface. Okay. Oops. What happened? So the volume that lies above that rectangular domain or region, but below, so here we're saying it's below the surface Z. Then this is basically, okay, our volume is the double integral, and R is my rectangle. And here I just plug in my function of two variables. and then this is D, A, right? That's it. That's the idea. Okay, I'm not gonna go through, does it make me go through Riemann sums? Oh, it does. So there is one example. I'm gonna go through this and then I'm done with the Riemann sum because I don't want to do more Riemann sums anymore. That's a calculus 2 thing, and I don't like it because it's too long. Okay, and we can also do it for a sum in definition 5. And we actually call this a double Riemann sum, and it's used as an approximation to the double integral. And if we notice how similar it is to the Riemann sum in 1 for a function of a single variable, if f happens to be a positive function, then the double Riemann sum represents the sum of volumes of columns, right? So if f is positive, the Riemann sum is the sum of volumes of columns. And it's an approximation to the volume under the graph of f. So it is similar to calculus 2 in some way, where if our real valued function f is positive, then it's the area under the curve. Here it's the volume under that curve or under that surface. So we're taking it into a 3D, right? Okay. Let me go ahead and just go to an example. And I'm also gonna do one here. And then we're gonna cut the video from there because I don't want it to be super long. So here we're being asked to estimate the volume of solid. Obviously, it's gonna be a solid. And that solid lies above the square. So here's our rectangle but square. And it has these dimensions. So it's 0, 2, and then 2, 0, right? Oh, my bad. Oopsies. That doesn't make sense. So that's a square, right? So that solid lies above that square, but it's below the surface, specifically an elliptic paraboloid. So we know what that is. It's an ellipse that has two traces of a parabola, two vertical traces of a parabola. This is equal to, or the equation of that surface is z equals 16 minus x squared minus y squared. No, minus 2y squared. Oops. So here we want to divide R into 4 equal squares. We want to choose the sample point to be the upper right corner of each square. So here's what we're going to do. We want to divide R into 4 equal squares. So we have a square, we divide it into 4 equal squares. And then we choose a sampling point. Right? And this sample point is going to be the upper right-hand corner. Upper right corner of each square. Right? And we're going to name this square some R sub ij. Right? That's how we're going to denote each square. And then from there, well, it's asking us to sketch the solid and approximate the boxes. I'm not going to do that anymore. It's not that I don't want to, but actually I don't want to do this. Specifically Riemann sums, I don't want to deal with that. But I'm just going to go ahead and show that picture of what exactly I'm referring to, and I'm going to explain it. So the idea is, oh shoot, there. So we have this xy plane, and then we have a square. So this is the square in the xy plane. It goes from 0 to 0, 2. So x is in between 0 and 2 inclusive. Y is in between 0 and 2 inclusive. What else can we say about it? Well, above it is an elliptic paraboloid. Now, I don't want to guess what that is, but here we just want to divide it into four equal squares. So there we go, four equal squares. And then the sampling point is the upper right. So if we look at let's just look at this rectangle or this region. What's the upper right corner? This one. Now let's look at, I don't know, this region. That's the upper right corner. Now we look at this region. Upper right corner. So you see the idea. Then we look at this. Obviously, it's going to be the upper right corner. Because in the previous one, we chose sampling points at random. I think it was a random sampling point. This was totally random. But there's one in each region R sub ij. But here we're specifically doing an upper right. We could do an upper left. Upper left would be this. We could do a midpoint, I think. That's a thing here. Because I did that in calculus too. Maybe something like this. And then there are like other approximations. We could do completely random points, whichever will give us the right or the most accurate approximation. I'm not sure in volumes. But in real valued functions, I think it was the trapezoid or something. We use trapezoids instead of rectangles. So maybe something like that. A trapezoloid. I don't know. What's the 3D of a trapezoid? Something like this. Anyway, okay, before I digress, just out of curiosity on my end. So what we're gonna do, okay, we're done with that. The squares are shown in that figure, right? The four squares. The paraboloid is the graph of, well, we already have it. And the area of each square is 1. How do we know? How do we know the area is 1? Well, this is 1. This is 1. 1 times 1, 1. Right? Okay. And then we approximate the volume of Riemann sum. So that's what we're going to do. So we have our volume. We do a Riemann sum. It goes from where to where. So from one of our, if we look back to our formula of the Riemann sum, we're going from, what is this outer sum representing? This outer sum representing, I'm not sure if it's, yeah, I'm actually a bit confused because I don't know what that represents in particular. Some I value, I is here. And then J is, I don't want to assume. But since I took a bit of scientific computing, I'm going to assume I and J refer to indices. And so I'm going to say, this is I, and it goes there. J, on the other hand, goes here. So I represents the number of rows, J represents the number of columns. And so this one represents the rows. This one represents the columns. This starts from I as 1, and then that one starts from J as 1. Okay, so from here, this is our I, and this is our J, right? Oh yeah, I'm right. Oh, wait a minute. Wait. Oh, I have it in reversed. Yeah, see here, this is R sub 1, 2, and then now this is R2, 2. Which means I represents column, J represents a row. So now here it's reversed. That's funny. Okay, but anyhow, we have the exact same thing. So this is I equals 1. That goes all the way to 2. Same for my J. Starts at 1, goes all the way to 2. And then my sampling points are, well, X goes from I y goes starting from j, and then my delta A is just 1. Right, so here we're just approximating a Riemann sum. And so let's plug in. So what is this Riemann sum? Let's solve it. We have f sub 1, 1. F sub 1, 1 is this first one, because they start at 1. And then multiply it by that change in A, plus f sub 1, 2. Oh, so here we're going to move the j first, right? So here, I'm going here plus here. Then that's delta A. I should have done this at the bottom. What am I doing? Because I know Riemann sums are big. I'm going to do this at the bottom. And then let me guess. F, since it reached that, now we have 2 sub 1. And then 2 sub 2. Right? Is that it? Yeah. Now I can factor out my delta A. Or I can just plug in the numbers I need. So F11, well, I solved for that, right? So F11 is something. F12 is something. I'm just going to go for it, but everything is 13 times 1, since my delta A is 1. 7 times 1. This one is 10 times 1. This one is 4 times 1. And all of that is equal to 34. And that's the volume of the approximating rectangular boxes in figure 8. And we can get better approximations if we put them all to infinity. So we get better approximations when, let's say, we increase the number of squares. And it starts to look more like an actual solid, right? If we use 16, 64, 256. And apparently the exact volume is 48 if we compute its integral. So here's how some approximations using Riemann sums would do it. Let me show that real quick. There. So as we keep on increasing our m and n, we're going to get closer and closer to the actual volume, right? Okay, let me do an example of that Riemann sum. I don't like Riemann sums, I'm going to be honest, in my homework, and I'm going to call it a day. So here we're being asked to, again, estimate volume of solid. And here it lies below surface. So what surface? Z equals xy. That's the surface. And above a rectangle. So here again, we just go for it. Here's our rectangle. It's the set where the set of all xy points. X is in between 4 and 10. Y is in between 4 and 8. Right? And so we're going to use a Riemann sum to take the sample to be the upper right corner of each square. And then we're going to use a midpoint rule. So this is something we haven't done in a while. And I think this might be a bit tricky. But let's go through it. So here we use a Riemann sum. And we're going to specify some values. We're going to say m is 3, n is 2. Sampling point is upper right. Okay. Okay, let's quickly do that. So again, we look at our rectangle. And then we split it. That's what we would do, right? We're going to split that rectangle Because right here we did split it into a couple of points, just like this one. Okay. We have to get something equal, right? Okay, let's quickly do that. Okay, so here I'm gonna draw. That's what I'm gonna do. I'm gonna draw the rectangle. So this one's gonna be something from the XY plane, right? Yeah, because it's 4, 10, 4 to 8. So here I start at 4. Oh crap, I don't know how to do this. Is there like a formula I could follow? Because it's hard to do it in 3D. Let me see. Because I don't think there is a formula. 0 to 2. Here it's nice because it starts from 0 to 2. Then you just have to do this. And then get all of those points. Here though, oh yeah, and then you just do a Riemann sum. Okay. So let me go ahead and MS3 question mark? 3 like what? No, we're actually given, okay, I think that was the helpful information. We're given that. So we could probably, because I need to draw to find the points. That's the thing. So okay, wait. So here we start off with 1, 1, and then we go to 1, 2. Then we go to 2, 1, we go to 2, 2. So this is the inner one, the N, then the outer one's a M, right? So for N, we have 2. So we have to slice this into 2. So let's look at our N first, right? So when you look at N, we slice it into 2. Let's say we make some box. Boom. Easy, right? We slice it into 2. Here, it's telling us to slice it into 3, right? And then from there, crap. Oh God, it's not a perfect rectangle. Anyway, let's pretend these are all equal. Here, ah, here my sample points are upper right, so I'm gonna look at these. Okay. Oh, but then look at this. This goes from 4 to 10, my X. My Y goes from 4 to 8. So this shouldn't be in the origin, actually. Should be somewhere else. Right? This is my Y. This is my X. It goes from 4 all the way to 10. This goes from, holy moly. So it's actually, oh, that was fine. And here we just put like a 4 and then okay. So this one's actually not at the origin. I don't know why I thought of doing that. This one's 8. So here's our rectangle. Then we look at our N. That's this one. We look at our M. That's this one. Right? Then we have our upper points here. So this is 4, 4. And then here we just kind of divide it. So this is 6. We kind of divide this as well. 6, 8, right? So this is 6. This is 8. This is 6. That's how we divide this equally. They're not drawn to scale, don't worry. Right. And then from there, our direction is we go up like this, add, go up like this, go up like this. And then we got the Riemann sum using an upper right thing. Okay. So let's quickly do that. Okay. So my V is the Riemann sum. So this goes from I to 4, my bad. This is I to 4. And this one goes all the way to 8. Because that's my outer. My inner one, however, or do I have it in reversed? Wait, my I was, here in this case, my I are columns. I'm pretty sure I go row first. Wait a minute. I know I go row first. Oh, shoot. I go row first. I do J first. Here, I'm gonna get dizzy here. Because they treat I. Oh, that's weird. Oh my goodness. That is weird for me. Here they treat I as a column and J as a row. So the way this thing moves is R1 to R2 to. So it's that first index that's moving. Oh my goodness. That's fun. So when I go to the right or to the left, I'm moving my first index. Anyway, I'll get used to it. This should be fine. Oh, actually, I'll just label it. So this is R. Oh, crap. I can't like label it, you know? How do, you do 0? No, you only went up to 2 because it's up to 2, right? 1, 2. Yeah, because I also have to take into account the change in area. Okay. Okay, yeah. Doing this for the first time is really annoying. So this starts from 4 all the way to 8. Wait. That's my I, right? My I is moving from. No, this is my J. No freaking way. Okay, so this is what's moving here. 1, 1, 1, 2. Let me take a screenshot of this. I can't. I can't deal with this. I'm gonna. Okay, this is really interesting. 1, 1, 1, 2. I'm just trying to get into the thinking. So here I start from my J going up, right? So this is me going up and down. Okay, let me just give some clues. Going up and down, that's J. Going left and right, that's I. Okay? So if I move left and right, I'm moving my I. If I move up and down, I'm moving my J. So here I start with my J. So this is actually J starting from 4 going all the way to 8. And then here it's from 4 going all the way to 10. Okay. And then I have my points here. So my F of X I Y J. Okay, I hope I'm actually getting it. Yeah, because here I'm gonna move all the way here, delta A. Moving all the way here, and then I get something. I'm trying to see, because I can't. I find this annoying to visualize actually. Oh my goodness. Okay. R11, R12. Then I go here. R21, R22. And so I go to here first. R F11, F12. F21, F22. So here my J is the one that's moving. And then here my okay, let me see. Now I go to my 2 for my I. To me, this looks kind of like a for loop, and it's kind of funny because it's a CS thing. So I go here, that's my J. Then I move to the next one, that's my I, then my J again. Anyway, it's okay. I just tried to think of it that way. Let me go ahead and see what I should get. So if I go here first, I'm gonna start off with here it's f of 1, 1. Okay. Here I should start off with f of 6, 6 delta A. I'm gonna add it to f of 6, 8. Then my change in A. And then I go to the next one. Now I go to 8. 8, 6. Then I do it again. 8, 8. Yeah, this is why I don't like Riemann sums. These things take way too long. Then 4. Or no, not then 4. Then 6. Then 8. Okay. And now the next issue. What's my delta A? I think it's just 2. Right. I don't know, I'm not super sure. What was the... Oh, goodness. This is why I don't like this. B minus A over M, that's my delta X. Oh, it's the change in X times the change in Y. So my change in X here is 2. Here it's 2. So my change in A is actually just 4 in this case. Okay, so I can factor out the 4 of everything and then just add them all together. What's my function? Please just be simple. Okay, it's xy. So I multiply 6 times 6, 36, plus 6 times 8, 48, plus 6 times 8, 48, plus 8 times 8, 64, plus 10 times 6, 60, plus 8. And I get something. 336 times 4, I get 1344. And that's my volume. I hope I got that one. Let me see, because I feel like I didn't. And here we're being asked to use a midpoint rule. So M is 3. Oh, shoot. M is 3, N is 2. And I put N and 8. M is 3, N is 2. Here I start from 1. It's just a notation thing. Oh, I don't mind. Yeah. Okay, cool. So if I were to try to like graph this out, so this is R11, and here I'm moving my J, right? Then I go back here, R21, R22, R31, R32. Whoops. I think that was how it worked, right? 1, 1, 1, 2. Then I go to the next thing, 2, 1, 2, 2. At least that's how I think of it. 1, 1, 1, 2, 2, 1. Yeah, yeah. It's basically that. I'm gonna hope we get. If we don't, that's totally fine. Oh, we got it. Oh my goodness. 1, 3, 4, 4. Okay. After all of that, bro, that was annoying. That was really annoying. That's why I don't like integral calculus. Okay, next we want to use the midpoint to estimate the volume of the solid. So here we want to use midpoint. To estimate volume of solid. And so what is this midpoint rule again? Well, we get the midpoint, obviously. So here, we get the midpoint of each of these things. So how does that look like? We basically get this middle thing. What is that? That's 5, 5. That's annoying. And we get the middle of everything, basically. So 5, 5, 7, 7, stuff like that. And then we multiply it to its area, or the change in area, which I'm assuming is the same thing. Midpoint. Yeah. And then we also multiply it to 4. So using midpoint, well, yeah, again, we just do 5, 5, and then my change in alpha plus 7, 7. My change in alpha plus, I think this was 7, 5, right? Then we keep going. So 7, 5, 7, 7. Oh, I just realized, why did I get 7, 7 here? 5, 5, 5, 7. I shouldn't get the same two numbers. So that's also an indicator that I'm actually missing something. Ay, ay, ay. Okay, and then we have 9, 5, 9, 7. Done. So I think that's everything, right? Okay, we basically add all of them to 4. Let me see. What is this? 5 times 5 is 25. 7 times 5 is 35. 7 times 5 is 35. 49, 45, 63. So that's what you get for multiplying or for memorizing the multiplication table. 25 plus 35 plus 35 plus 49 plus 45 plus 63 times 4, 1008. And we're done. Yeah. And by calculus 2 standards, usually the midpoint rule is more approximate or it's better than a right upper right corner. Usually it's better, right? Let me just submit, see what happens. Okay. Am I gonna do more Riemann sums? Because I really don't want to. It's more of iterated integrals. I don't know what that means. I'll learn it. Volume of solid. Okay. Yeah, that's pretty much it for Riemann sums. I'm not gonna go into it again. Hopefully not. Maybe in future courses, but yeah, this is something I really don't like. I don't like approximating things too much. It's fine, but I would rather let a computer do it and not me. Anyway, that's it for this video. I hope you guys enjoyed, and I'll see you all in the next one.